Hello everybody, my name is Andy Shevchenko. I work at Intel on the Linux kernel drivers development for new SoCs and ACPI based platforms. Today I am going to tell about ACPI overlays and how they can be utilized on embedded platforms when prototyping a new device. ACPI is a fully featured framework to serve power management needs along with helping an operating system, for example Linux, to discover devices or extend the features for the devices on the self-discoverable buses. What is this for? ACPI stands for Advanced Configuration and Power Interface. It has been established in order to solve a few problems. The main point of interest is the device discovery and configuration mechanisms to cover more peripherals such as SPI, I2C, and support of arbitrary device properties. These are available starting from version 5.1 of the ACPI specification. Roughly speaking, ACPI is a connector between firmware and operating system worlds, provided by firmware in the form of data tables and definition blocks. It has a dedicated interpreter that runs on the OS level, where an ACPI virtual namespace has been created. The ACPI has a domain-specific language, ASL, and initially all definitions are described in its syntax. Before supplying to the interpreter, the ASL needs to be translated into a bytecode. Here we may see an example of the source listing and bytecode for the SPI GPIO expander. The diagram shows similarities between ACPI namespace and device tree. When an operating system runs, it parses the extended root system description table, followed by others, including the so-called differentiated system description table, or DSDT, and number of SSDTs. SSDT stands for Secondary System Description Table and represents a continuation of the DSDT. The SSDT is comprised of a system description table header followed by data in definition block format. This allows the OEM to provide the base support in one table and add smaller system options in other tables. For example, the OEM might put dynamic object definitions into a secondary table so that the firmware can construct the dynamic information at boot without needing to edit the static DSDT. But it comes also with limitations. By definition, SSDT can only rely on the DSDT loaded prior to it. And additional tables can only add data. They cannot override data from previous tables. Note that a table can add information to any place in the existing ACPI namespace. There can be multiple SSDTs present. After the OS loads the DSDT to create the ACPI namespace, each secondary system description table listed in the XSDT with a unique OEM table ID is loaded in the order presented in the XSDT. As of today, the sources of the tables can be firmware, bootloader, and 3 additional sources supported by the Linux kernel in the form of trailer of initramfs. Note the limitation as of 64 tables at most, EFI variable, or blob provided via config.fs. The first two of them are boot time options and the last one is runtime specific. The SSDT overlays are produced from small excerpts of the ASL code that can be added into the system by the user at boot time or runtime. This is mostly useful during the prototyping phase of a platform in order to quickly change the configuration without rebuilding a firmware. Let's consider the connection of the Solomon OLED display. It is an SPI device which requires a couple of GPIO lines. That's why it needs to be described by SPI resource, chip select, bus frequency, and host controller reference. And GPIO resources for data command and reset signals. Additional device properties, such as names for GPIO resources, compatibility string. Note there is no dedicated ACPI ID for this device. Screen dimensions and bus width for the driver have to be added. All pieces together may be unified into device object. Note that the special ACPI ID PRP001 tells Linux kernel to use the compatibility string. The last part is to rope the device object by a definition block which will represent a complete SSDT. The easiest way to load the SSDT at boot time is to attach it to the initramfs image. First of all, compile the ASL to produce an YAML. Then archive it and attach the existing initramfs to it. Note that the uncompressed part should go first in the resulting blob. The very same compiled AML can be loaded via config.fs as can be seen during the demo session. A few words about the platform used for this demo session. This is Intel Edison module with an updated U-boot in order to enable ACPI. The module is connected to the Arduino breakout board. This board has an external pin control based on discrete components, such as I2C GPIO expanders. The environment has to be prepared before the instantiation of the devices. This can be achieved by mounting config.fs and loading a corresponding ACPI driver. The first step after that is the instantiation and configuration of the external pin control. The device to be connected next is the LCD 16:2 panel attached to the GPIO line. The following device is Solomon display, which is connected to SPI bus. Oops! Suddenly, the wrong rotation appeared in the table. Without kernel recompilation or even reboot, it's possible to fix this. It needs the step of ASL compilation to be performed. When the new AML is available, it's easy to unload the previous one. Remember the caveat, so that unloading tables sometimes may not succeed. And load back the fixed one. To continue with the topic, the following resources will be useful. First of all, it's ACPI specification version 6.4 as of today. Supported documents on site uefi.org. In-kernel documentation specifically related to SSDT overlays. Additionally, it would be good to look into a couple of repositories. One of them is Meta ACPI project, and another is our fork of buildroot, which brings a few scripts to make everything easier when you create an image based on buildroot. Thank you. If you have any additional questions, please do not hesitate to ask.